In this lecture, we'll learn about using ice tables for equilibrium calculations. If we review several experiments where the initial and equilibrium concentrations of hydrogen, iodide, and HI gases are measured at 445 degrees Celsius, we see that we can start with all reactants and no product, all product and no reactants, or some mixture of reactants and products. But the value of K sub C doesn't change. We see that Kc is a constant at this temperature and does not depend on the initial concentrations. Knowing this, we can find equilibrium concentrations and K sub C from initial concentrations in a reaction mixture. Does this mean a road trip to IKEA for a new piece of furniture? Actually, an ICE table is an acronym for the arrangement of data. Specifically, the initial concentrations plus the change in concentrations to equal the equilibrium concentrations. Let's walk through an example so that you see what I mean. Suppose that you start with 0.100 molar each of sulfur dioxide and oxygen. At equilibrium, you find that the concentration of oxygen is 0.0750 molar. How can we calculate the value of K sub C from this information? First, we'll drop our equation into the top line of an ice table. Next, we'll fill in what we know. The concentrations of sulfur dioxide and oxygen are both 0.100 molar, but the problem doesn't say anything about the initial concentration of sulfur trioxide, so it's safe to assume this value is 0 initially. We're also told that the equilibrium concentration of oxygen is 0.0750 molar. We have a completely blank change line in our ice table, so let's think about how to fill that in. Since we have an equilibrium reaction, we can't say that all of the oxygen or all of the sulfur dioxide reacts to give products. What we can do is to state how much of each reactant is consumed in terms of X. That is, if I use up X moles of oxygen, I have to use twice as much, or 2X moles of sulfur dioxide. I see that I'll also produce 2X moles of sulfur trioxide for every X mole of oxygen consumed. Adding that information to the table, we're able to contemplate a strategy for finding X because we know that I plus C equals E, or in this case, 0.100 minus X equals 0.0750 molar under the oxygen data column. Setting up this algebraic equation, we see that X is equal to 0.0250 molar, which we can fill in under the SO2 and SO3 columns to find the equilibrium concentrations. We see that the concentration of sulfur dioxide at equilibrium is 0.100 minus 2X, or 0.100 minus 2 times 0.250 equals 0.500 molar. The concentration of sulfur trioxide at equilibrium is 0 plus 2X, or 2 times 0.250 molar to give us 0.0500 molar. Now we're ready to put it all together to calculate the equilibrium constant, K sub C. Plugging in the equilibrium values, we see that K sub C is equal to 13.3. If you had any questions about how we step through this example, please ask questions. We'll be using ice tables for the next several chapters to solve problems, so it's a good idea to get comfortable with them sooner rather than later.